Alright, welcome to another video. The main focus will be ability. What to be dependent probability. What is conditional probability of an event A occurring, given that another event B already? It also tells us how the probability A changes when we know that B has occurred. Alright, so the formula for finding conditional probability of A given that B has occurred. Probability of A divided by probability, provided that probability of B greater than 0. Also, we want to find probability of B given that A has occurred is given by probability A intersection that A it also provided that A is greater than. So you know that probability of A intersection B is basically probability that both A and B will occur. And here is probability that B has occurred and probability that A. So the whole idea about conditional probability, I have a Venn diagram here. I have point A, B. Then here is probability of A intersection B. So our main focus is on, and we have to find probability of a given that B has occurred is trying to find what portion of A is in what B. What portion of A what given as in this portion what is in. Also, if you have to find probability of B given A, meaning that if you have A given, what portion of A or what portion of B in what A? That's the whole idea about conditional probability. Also, we have to look at some key properties that probability of A given B is not equal to probability of B in A. Bear in mind, probability of A given B is not equal to probability of B given A. Also, if we are saying that A and B are independent, that is, A doesn't influence B or B doesn't, then can we write it as probability of A given B the same as probability of A? Also, probability of B given A the same as probability of B. Since now here A is not depending on B, the same as probability of A, and here too B is not also depending on A. So we can also therefore write that if they are independent, then probability of A intersection equal to probability of B intersection A times probability of A. Or we can also say that probability of A intersection equal to probability of A given times probability of, let's take note. Also, when are we to use conditional probability? Here are some clues you need to know. So we use conditional probability when we are given a condition or a filter, Also, it reduces the what? The total sample space to what? To a subset. So this is what I mean. Here we have the whole area being the total, but if you are being given a condition or if you are dealing with condition probability, as I said earlier, we are looking at what portion of what A do you have in B. That's if you have to find probability of what A given B, probability of A given B. We have to find the portion of what A, which is in what in B. So when you see some words like given that, if it is known that, assuming that, and all these kind of things, they mean that we have to use the conditional probability from use our answer. Let's look at some illustration. So illustration 1. Suppose that we have two events, A and B. Probability of A is given as 0.5, probability of B 0.6. Probability of A intersection B is 0.4. Find probability of A given B. And we all know that probability of A given B, probability of A divided by probability. And probability of A intersection B 0.4, 0, and probability of 60. So now we have 0.4 divided by 0.6 is giving us 0.67. So you can say that we have 67% All right, let's solve question. B part is saying that find the probability of B given A. Probability of given A is given by probability of divided by probability of A, which is 0.5. A. Are A and B independent? I O. We learned a previous video for two events to be then the intersection as probability intersection B equal to multiplication of the product of our probability. Now we know that probability of was given 0.40. Now let's find probability product of these two. Now probability of A, which was so now probability of A 0.50 0.5 0.6 0.3 You can see that the product of these two probabilities not equal to, therefore these two events are not independent, are not. Right, let's solve the next. A slot machine, Elmina has hold facility. The gambler experiment says to see their success rate is, if their success rate is higher when they use hold compared when they did not use. The result from 120 plays can be summarized as follows. We are asked to find the probability that gambler holds wins given that they held and lost. Held given that they won. So I've used some clues, or we did some that given that, assuming that, so all these ones, the C now. Right, so now let's solve this question. What is the probability the gambler holds? So if you hold, you can either win or lose. And let's find the total here. Here you can apply the marginal probability. We are 14, 36. Total number of hold is 50. And the total number of not hold also 70. Giving us a total of 120. Have it here. Then you have to find the total number of win. If you win, you can hold and win or not hold and win. So we have 14 plus 10, 24. Then 36 plus 60, also giving us 96. We add the 24 and the 96, also getting 120 as given. What is the probability that the gambler holds? You have to find probability that the gambler buy. And either hold. So let me use two alternatives. We can either hold and win, or and hold now. What is the probability that person hold win? You are 14 divided by the 2, or in probability is addition, as you hold and you lose, which is 36 divided by 120. Five. Alternatively, you can use a total. So we are holding, then we have a total of what? 50. So simple. Divided by. All right. Now, what is the probability the gambler wins? Probability that you win. Let's come to it. So if you win, you can hold and win, or not hold. We have a total number of 24. 4 divided by 120 as 1 over 5. Or you can take them separate. So if you are winning, you can either hold and win. Given as 14, or alternative, you can solve it. 14, or you can not hold and still win, and you have 10. 24, 120. Let's come to the C. We have to find the probability that the gambler wins, even that they held. Find the probability that gambler, even that held, equal to probability held divided by probability. So here given becomes the what? The denominator. Anytime you have been considering that the given becomes the. Now let's find probability of you winning. So when you win and you hold 14, you have 14 over here. You have 14. Divided by hold, the total number of hold. Because when you hold, you can either win or lose. Total number of hold is 50. Now we have 14 divided by 50, giving us 725. So in a Venn diagram form, it's more like here we have this. We have win and hold. Yes, 14. Now you know that this 14 here is those who win and hold. But here, because we are limited to what? 8. Now what portion of win or those who hold win, which are in what? 8. That's what the conditional probabilities class. Let's do the next question. Held and lost. Held and that's the D part. Held, lost. So if you held and lost, the probability of held. So if you hold and you lose, you have 36 over here. 36. This is not a conditional probability. Divided by the total place. So we're going to have 36 divided by 120, which is 3 over 10. 3. Now, the last one, held, given that they lost. You have to find the probability that they held, given that they won. Probability of held divided by 1. So when you hold win, hold and 14, you are restricted to wins. Total number of wins are 14 divided by Let's solve the last question. Let's solve the last question. 3 unbiased coins are tossed. 3 unbiased coins. What is the probability of 4 heads, 2 heads, 1 head, at least 1 head, at least 2 heads, or tails? So if you toss 3 coins, you would have to determine the number of outcomes. You have to determine the number of outcomes. You can use the formula n raised to the power k. Determine the number of outcomes you get. Where n is the normal. When you toss a coin once, you know that you are getting what? Two outcomes, head or tail. And A is the number of repetition, number of times you are doing the trial. So if you have 2 outcomes by tossing a coin, then you can have how many coins? Toss 3. And take note that we tossing 3 coins the same time, same as we tossing 1 coin 3 times. Let's bear in mind. Now you're going to have 2 times. The total number of outcomes by tossing 3 unbiased coins is going to be 8. Now let's list the outcome. You can use a tree diagram, or you can do list by set notation for space. We're going to have 8, 8, 8, 8, tail, tail. Have tail, head, head, tail, head, tail, 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 head, tail. Have a sample. You can also use Venn diagram. That I'll do that at the end of. So A. Now we have number of samples. Now probability that 4 head. Now probability that we are getting are all heads. All the 3 are heads. Of 1 divided by 8. Then probability that at least probability that 2 heads. That's exactly 2 heads. Probability of we have 1 here. Have another 1 here. Last one is we have 3. Probability that 2 8. 1 head. 1 1 head. We have 1 head, another head, another 3. At least 1 head. At least 1 head means 1 or more. 1 or more heads. 1. Oh, here contains 1 or of these. So we have 7 out of 8. 7 out of. Then the E. At least 2 heads. At least. At least. Meaning that 2 and more. this one we have 1, 3, 4. We have 4 divided by A. 0.5. We're looking at least 2 or more. Then last one is F. All tail. Obviously we have 8. Thank you. Subscribe for more videos.